experiment consisted of an open channel flume where we had 3 different surfaces. The first one was plastic, the second one was turf grass, and the third one was rock. And as you can see in the diagram, we calculated the different depths at y1, y2, and y3. And these depths were then averaged, because we took a total of 5, to then calculate Manning's N for the 3 different surfaces. And H over in the right-hand corner designates the height of the water over the edge of the flume, and that was used to calculate the flow rate using the Weir equation.
For the Weir equation, Q equals 3.32 times L times H to the 1.5 power. Q equals the flow rate, feet cubed per second. L equals width of the channel in feet. H equals height of water in feet. Q equals 3.32 times 1.5 feet times 0.24 feet to the 1.5 power. And the answer we came up with was 0.59 feet cubed per second.
After the Weir equation, we use Manning's equation, which is Q equals 1.49 over N times A times R to the 2/3 times the square root of S. In Manning's equation, Q equals the flow rate in feet cubed per second. N is the coefficient of friction. A equals the area in feet squared. R is the hydraulic radius in feet. And S is the slope in feet per feet. The equation at the bottom is how we figured out Manning's N. So we have to divide Manning's equation by Q, and then that's how we figure out what the N, the coefficient of friction, is for the 3 different surfaces. For the plastic surface, we first had to find the area and the wetted perimeter in order to calculate Manning's N. So for area, it is the width of the channel times the depth of the water, which we found to be 1.5 feet for the width and 0.34 for the depth. And that came to 0.51 feet squared for the area. And then our hydraulic radius is the area over the wetted perimeter, which then simplifies to the width of the channel times the depth of the water, divided by the width plus 2 times the depth. And that came out to a total of 0.23 feet for the hydraulic radius. And then next we had a 1.5% slope, and we had to convert that into feet per feet for slope. And so that came out to 0.015. And then for our Manning's N, when we plugged in all of the numbers, we came up with 0.059. And our velocity, which is the flow rate Q divided by the area, so that came to a total of 1.16 feet per second for the velocity on the plastic surface. Next, for the grass surface, we have an area of 1.5 feet times 0.35 feet. So our area came out to 0.53 feet squared. And our hydraulic radius came to a total of 0.24 feet. And our slope was constant throughout the experiment, so that stayed at 0.015 feet per feet. When we plugged that into Manning's equation, we got our N, the coefficient of friction, to be 0.063. And then for our velocity, we did the flow rate over the area, which came out to be 1.11 feet per second. And finally, for the rock surface, we had an area of 0.62 feet squared when we plugged in the width, which was 1.5 feet, and the depth of the water, which was 0.41. And then for the hydraulic radius, we came out with a value of 0.27 feet. And again, our slope stayed the same, so it stayed at 0.015. When we plugged in those values for Manning's N, we came up with a value of 0.079. And for the velocity, which was flow rate over the area, we came up with 0.95 feet per second. So in conclusion, you can see the velocity and the Manning N values for both the plastic, grass, and rock surfaces. And in the velocity column, you can see that the plastic had a higher velocity than either the grass or the rock, and it also had the lower Manning's N, which is the coefficient of friction. So based on our results, we could conclude that with a lower coefficient of friction, we were able to then see a higher velocity, which is true because with that higher coefficient of friction, the water doesn't move as fast over the grass and the rock surfaces.